Water Program Director for the Isaac Walton League of America. The Isaac Walton League is a national conservation organization, and our mission is to conserve the soil, air, woods, water, and wildlife of the country. We are going to demonstrate the Virginia Save Our Streams Rocky Bottom monitoring method. This is a method that you use in streams that are fast moving and have riffles where water bubbles over rocks that are cobble size, about 3 to 12 inches. Usually we'll find these streams west of the I-95 corridor. A few things to keep in mind when you are monitoring streams is that you want to, if you have several sites on the same stream, you want to keep those stations about a quarter mile apart from each other. Reading of the water temperature. So you can take your aquatic thermometer and hold it under the water surface. You want to hold it there for at least a minute to allow it time to read the temperature. You want to make sure that when you're reading the temperature that you do that before you take the thermometer out of the water, because you want to make sure that you are getting the water temperature and not the air temperature.
Alright, I am measuring the turbidity of this creek right here. Let's put it on. 220.
Did you see it?
Yeah, 220.
220 parts per million. Yeah.
Okay. So you're going to leave it in there until it starts to slow down and then count to 3.
That's for turbidity.
Riffle to monitor, it's important to get a good quality riffle. What you're looking for is an area where the water is bubbling over the rocks. You'll see those white cap bubbles. The rocks are cobble size, which means about 2 to 12 inches, or the size of lemons to cantaloupes. And you want to make sure that you have pretty easy access to get into the stream to where your riffle area is. You're going to hold the net, position the net in the stream, and lean it backwards so that as much water is flowing into the net as possible, but make sure that water is not coming over the top. You also want to make sure that water is not flowing under the net. So right now we are putting rocks on the bottom of the net to secure it. And it's important to take those rocks from outside of your sampling area, so outside of where the 2 poles of the net are, and to rub those rocks off thoroughly before you put them in front of the net to make sure that there aren't any bugs from outside of your sampling area getting in. So once you've done that, you're going to monitor the rocks that are in a 1 square foot area in front of the net, and that involves rubbing the surfaces of the rocks vigorously under the water. And the first time you do this, you're going to do this for 20 seconds. So you're going to rub rocks for about 15 seconds, and once you have rubbed as many rocks as you can in that time, you will then disturb the bottom with your fingers. You want to clean off the rocks that are anchoring the bottom of the net, so that any bugs clinging to those don't get in your sample, and then pull the net toward you and lift up to make sure you keep all of the bugs in there. And then bring your net back to the table where you can lay it out and pick the bugs off and sort them. Once you have the net on the table, you're going to want to look for all of the bugs that you can find and pick them off and identify them. It helps to first look for any large critters that might be making their way off of the net to make sure you don't lose them. So you want to monitor the edges of your table and watch for that. It also can help to go through any debris. You may have some rocks or leaf litter on the table, so you can use your spray bottle to rinse those off, and once you're sure that there aren't any bugs clinging to them, you can dump those off so they're not in your way. One thing that's very helpful is to use your ice cube tray to sort the bugs into look-alike groups, or if you are able to identify any of them while you're picking them off the net, to make sure you are putting the bugs that go together in the ice cube trays. This will help make it easier to identify bugs later and also to count them when you're completing your data form. So remember that you may need to collect your bugs from more than one part of the riffle or from more than one riffle in your monitoring area. And you want to be sure to always start from the downstream section and work your way up. That ensures that any disturbance that you're creating by walking in this stream and collecting your bugs isn't going to affect the next sample that you take. You want to make sure that your net is clean before you take your next sample. So be sure to clean it off thoroughly in the stream, so that when you take the next sample, you're only looking at bugs from your new sample area.
Here we are at Lullwater Creek, an urban stream in Metro Atlanta. We've come here to sample for dissolved oxygen, an important indicator of the stream's ability to support biological life. A healthy stream tells us we live in a healthy watershed and a healthy environment. Tara Mintz is going to demonstrate how to collect the sample, preserve the oxygen level, and titrate the sample. We chose this site because it is a representative segment of the stream range. Plus, it has legal access and it's easy, safe, and waitable. She chooses a safe spot on the bank to lay out her kit. There's the waste jar. She will pour all of today's sample water and chemicals into the jar when she's finished. Never pour them into the stream or on the stream banks. Now she reviews the directions card and checks her kit. She goes to the center of the stream where it's deep enough to get her sample. She faces upstream. First, she rinses the sample bottles with stream water twice. Then she collects the samples. Watch how she submerges the bottles. When both bottles fill completely, she caps them underwater. This step is important to ensure there are no air bubbles in the sample that will alter the reading. Now that she has the water, she's going to turn both bottles upside down to check. Ah, she has an air bubble. So she has to dump the water in both bottles and recollect the samples. She's pulled new samples, and this time, no air bubbles. Before continuing, Tara reviews the directions one more time. So she dumps all of the sample liquids left in the bottles and the vials into the waste buckets. Cap the bottles, put them back in place.
Hi, I'm Zach Samsel and this is Gabe Acosta, and today we're going to measure stream flow by floating an orange here along Ackerman Creek. Hi, I'm Zach Samsel from Thinoleville Pomo Nation Environmental Department, and today we're going to measure stream flow, aka discharge, which is the amount of water that's flowing between a cross-section at any given point. Stream flow can vary depending upon the amount of rain, snowpack, and whether or not it's the warm or wet season. Having said that, we're going to measure the stream flow with some tools that you might have at home and the help of our special assistant.
Hey guys, Gabe Acosta. So today we're measuring the flow of a stream. Flow is important because it defines the shape, size, and direction that the stream is going to take. This is important in water quality and habitat location.
And let's not forget that stream flow and velocity help us to understand what type of organisms live within the watershed, which helps us understand their different migration patterns and spawning areas. With that in mind, let's get started. The first thing that you want to do is mark an area along the creek. We used camping stakes and a string to mark the beginning line, and then 20 feet away from there we measured another string, and this is basically going to be our racetrack, if you will, where the orange is going to float and we're going to time it. After you've strung the strings, we measured it and then divided that by 4 and marked it into 4 even intervals that are marked right here. That's going to help us to get the average depth of the creek by using a yardstick. Once you have both of the lines marked, we're going to go back through, we're going to check the depth at each of these, and we're going to write it down on the handy EPA stream flow calculation sheet. Now we're going to go to each one of these 1/4 intervals and check the depth of the creek so that we can take a composite average that's later on used in the calculation. And then obviously each of the stakes at the ends are zeros. We'll get deeper into the calculation once we've actually timed the orange. Now comes the fun part where we're going to float this orange and measure the amount of time it takes to travel from this string to the next one. Are you ready? Don't go too fast, buddy. Boom. And that's all it takes, folks. Now it's time to do some math. Let's take this show inside.
Now that you've filled out the EPA data form, we're ready to figure out the average cross-sectional area by using the data from the data form. We're going to start out by calculating the total width and then calculating the total depth. In calculating the average depth, we're going to take the total depth and divide that by the 4 intervals we marked on the line. And that gives us a total of 0.81 feet for the average depth. Then we take the total width, multiply that by the average depth, and we get our number for section 1. And now we're about to do the same for section 2. We're going to total up the total width, and then we're going to total up the total depth. Just like last time, we're going to take our total depth and divide that by the 4 intervals, and that'll give us the average depth. Then we take the total width, multiply that by the average depth, and we're almost ready to calculate A. Now we take the figures that we got for section 1 and section 2, divide those by 2, and that gives us A, an answer of 18.9 feet squared. Now we're going to calculate L, which is the length of the stream reach. The next part of the equation is determining the coefficient. It'll be 0.08 if your stream has a rocky bottom, and it'll be 0.09 if the stream has a muddy bottom as per the EPA guidance. Now we're going to determine the average travel time by totaling up all 3 of the timed runs that you did along the stream to determine the average time for all 3. Total them all up, divide it by 3, and you've got your average time, and that figure will be T. So to do a quick recap, A is 18.9, L is 20, C is 0.08, and T is 43. And now we're going to calculate flow, which is the average cross-sectional area times the length times the coefficient divided by the time. And that ends up giving us an average stream flow of 0.7 feet cubed per second.